All right, great. So wanted to start off just with some logistics stuff to get things started for today, some reminders. We got our presentation, so we're going to shift gears. Next week is the start of our sort of seminar half. As I kind of told you, it's kind of half and half with the lectures, me giving lectures versus you all giving presentations. So next week is when we're going to start our student presentations. I think all but 2 or 3 of you have emailed me about a date. And if you, there's still time, so if you want to email me, the Canvas is up to date, so if you click on these student presentations, it'll tell you, right, who's presenting. This date is full, so the 24th, I believe, is filled up. But the other 2 dates still have some slots, which also means that there are, 2 or 3 of you who have not claimed those slots yet. So if you want to claim a slot on the 22nd or the 29th, send me an email probably tonight. Because tomorrow, those 2 or 3 people, I'm just going to assign them the spots. And again, I'm not mad about that. I'm just trying to give you the opportunity to claim a date if you want to claim a date. If you don't want to claim a date, if you don't care, then fine. I'll give you one tomorrow. And I'll send you an email letting you know what day I signed you up for. Some of you have not picked a paper. Some of you have claimed a date but have not yet picked a paper. I would like to know that soonish as well. Not necessarily today, but hopefully, sometime in the next couple days, you'll have a chance to sit down and finalize your paper selection. I've had some conversations with some of you about this, and some of you have picked your papers, and I've tried to include that information as well. So, if the papers have been claimed, you'll see a date next to it on that list. That means somebody's claimed it already. They're planning to present on that date. But there's still plenty left to choose from, and you're welcome to go source your own as well if none on the list are speaking to you. So just wanted to make sure everybody is aware of those things coming up. I want to remind you all as well that these student presentations are going to be on the exams. So, please come, please take notes. The exams are open notes. I hope you're taking notes on everything, basically, so that you have that for the exam to make it as easy on y'all as possible. And then I also wanted to chat with you about the homework assignment, because that is coming up. The first due date is at the end of this week. How's that going for y'all? You feeling pretty good about it so far? Anybody not? Anybody feeling anxious about it? Anybody have any questions? Anybody have any issues or anything that you would like to chat about regarding the homework? Just to kind of give you a feel for where I hope you all have at least looked at it and picked out which problems you're focusing on. Maybe even developed some methods for collecting data, right? Or even collected some data by this point in time. Maybe not all the data at this point in time, but there's only 4 days left. So at this point in time, I would hope that you're pretty close to the data collection part of the assignment, if not already working on the data collection part of the assignment, so that you have enough time to properly write up a report and make the graphs with that data by Friday. If you're running into troubles with scheduling, if you're worried you're not going to make it in time because you're super busy at work this week or whatever is the case, there is some flexibility there, right? I think I have to do it like 5:30 on Friday, but let's be honest, I'm probably not even going to look at them until Saturday. So, not to say that you should stay up all night for that. Sounds like a terrible way to spend a Friday night, in my opinion. And I love this stuff, so don't do that. But if you need an extra day or two, just give me a heads up. There's definitely flexibility. There's not infinite flexibility, but there's some flexibility. So I don't want you to feel like you have to submit subpar work. If an extra day or two will get you to where you need to be, just give me a heads up. I'll work with you. We'll figure something out. I know everything is crammed together. That's just kind of the nature of these summer classes, right? I'm trying to manage that as much as possible, but so far I'm not hearing anybody complaining too much about it, so maybe I'm the only one who's worried about it. But if it does become a concern, please let me know. I don't want you to feel like you're drowning. I think that's it regarding logistics. This week, the topics, you can see we're going to be diving much more into the parallel world, because homework 2, which I know we're not even done with homework 1 yet, but homework 2, you can see we're going to be kicking off next week. It's going to be a parallelized program this time around, so we need to kind of set the stage for how to talk about parallel programs and how to design parallel programs and how to, on Wednesday, we're going to be taking a look at a new tool that is going to help us profile parallel programs, because the profiling tools that we've looked at so far, gprof and perf, well, more gprof than perf. Perf is a more modern tool than gprof is, but they have some limitations when it comes to parallel programs. So we're going to look at a new tool on Wednesday called TAO, which is a profiling tool specifically intended to work with parallel programs. It's going to become almost essential for basically all of the 3 assignments after the first one, since the first one's not a parallel program, but the other 3 definitely are parallel programs. So that's the goal for Wednesday. Today, unfortunately, well, maybe more unfortunately for me than for you, is more of a lecture-y, heavy day. Wednesday is definitely going to be some lecturing, but also some hands-on playing around with TAO, getting your hands dirty, and maybe even talking about the next homework assignment, even though the first one's not even due yet. Might kind of kick off the second homework assignment on Wednesday. So Wednesday will hopefully be a bit more active than today will be. But we have 2 topics on our agenda today. Before the break, I'm going to talk about designing parallel programs. We're going to start talking very generally about designing parallel programs and work our way towards more and more specific, concrete examples towards the end of that talk. And then after the break, we're going to talk about speed up and actually some other different metrics as well, which we use to characterize the performance of our parallel programs, which is going to come in real handy when you're talking about the performance of homework 2 and 3 and 4 in the coming weeks. So let's go ahead and hop into the first one here about designing parallel programs. So the goal here is to think about, I think most of us have good enough programming experience now where if we're faced with a problem, we can tackle it using the tools in our toolbox, right? We've got a whole bunch of them. My mind thinks to intro stuff because that's just what I'm used to teaching. But my intro students, I'd be like, remember your loops, your if statements, your methods, right? Those are the tools that we have in our toolbox. How do we put all those together in the right way to solve our problem? And of course, more advanced concepts like objects, inheritance, and interfaces, and all that fun stuff too, right? But when it comes to designing parallel programs, yes, we still need to use those tools, but it actually takes a little bit more thought, a little bit more care, because we need to consider how that program is going to be executed, not just on one machine, but across many different machines, and the various hurdles and the various complications that come with doing that. So there's sort of a generalized process for forming these kinds of programs, and it's really, I don't think this is any different than writing sequential programs. It's successive refinement, right? Try it, see how well it works. Is it going to work the first time? Probably not. So let's tweak it a little bit more and try it again, and just keep refining that process over and over again until we get it right. We're not going to necessarily catch every problem the first pass through. It's very rare if that happens. You probably have had the same feeling as me, where if something works on the first try, you're like, that's not right. Nothing ever works on the first try. So the same thing is true here. It's just the problems that we're looking at are different than simply forming an algorithm. The problems that we're talking about here are things like decomposition. So how do I break that problem into smaller pieces that can then be distributed across our various boxes, our various cores, or whatever the case may be? How do I take those pieces and make sure they're mapped appropriately to minimize the amount of communication that needs to happen? That's another kind of problem that we're interested with parallel programs that we don't really have to think about with sequential programs that are just running on a single thread, a single process, a single core. We have to balance the workload. That's actually a very important part of any parallel program. If I have 1,000 cores and 10 of them are doing 5 times the work as the other 90, well, that's going to reduce my effectiveness, right? Because 90 of those cores are going to finish real quick, and they're going to be waiting on the other 10. Or if I could balance it more evenly, that's going to squeeze more performance out. It's going to be a better use of our resources. Communication. So there's almost always going to be some form of communication And that's regardless of paradigm. Shared memory programs communicate by writing things into that shared memory location, so another process can read it back out. When we're doing the distributed paradigm instead, that communication is a lot more explicit. Send a message from point A to point B. That communication is always going to be there. How can we reduce the amount of work or the amount of overhead by communication? And then also, sometimes parallelization introduces extra work. Sometimes decomposing the problem, for example, requires some thought, requires some care. I have to compute this core is responsible for this part of the problem, and this core is responsible for this part of the problem, and this core is responsible for this part of the problem. That's extra work that I don't have to do if I'm just shoving it all through one core, right? So sometimes the very act of writing a parallel program introduces extra work for us. So how can we minimize those requirements? The fact of the matter is that if we look at any one of these in isolation, we can of course try to minimize it, but if I, for example, try to do the best job of balancing the workload, chances are that's probably going to spike these other two in some way, right? That's the classic trade-off that you see in basically anything relating to computing. It's always a trade-off. So what we're really trying to do is not just necessarily minimize all three of these things, but try to balance them across each other as well. If my workload is perfectly balanced, but that requires me to send a bajillion messages to all my cores, well, maybe if I unbalance the workload a little bit to decrease the number of messages, that might be a trade-off that's worth making. And there is no hard and fast rule that's going to work for every single parallel program. Again, you're just going to kind of have to give it a shot on your particular problem, profile the results, and then if they're not adequate enough for you, or if you suspect that it can be done better, you're going to have to turn the knobs a little bit and try it again and see what the next results are. So it's very much an iterative process. But none of these things really rely on the actual architecture themselves. So then once we get to the architecture itself, that requires some additional work. Now we actually care about, is this a shared memory machine? Is this a message passing distributed memory machine? And how do we then, ensure that our code is operating in such a way as to perform the best that it can on that particular architecture using that particular paradigm. So, yeah, I think I've covered everything that I need to on this slide. So let's take a look at then. This is a platform agnostic, program agnostic view of how to design a parallel program, right? I'm not talking about any specific machine. I'm not talking about any specific problem. I'm trying to provide just a generalized view of how we design parallel programs. And once we get to the end, I'll show you some actual concrete examples of parallel programs. So the first thing to do is to perform decomposition. So take our problem and decompose it into smaller problems. One of the easiest ones to talk about, because it's one that I know you've been looking at somewhat recently, would be like matrix multiplication. So for a matrix multiplication problem, the problem is I got two big matrices and I want to multiply them together. How could I decompose that? I could decompose it into rows, right? So one task could be a single row. So, or it could actually be a group of rows. So that task size is variable, and it might be worth trying various task sizes to see how that affects the load balancing, the communication, etc. But we need to make a choice. How can I take this problem and decompose it into smaller chunks? There's lots of ways that we can actually think about this. I described one way with the parallel, with the matrix multiplication example. Is this? Oh, no. That top part is I was expecting a different slide here. Did my slides get out of order? Oh, no, I'm sorry. My apologies. I'm just one slide ahead of where I thought I was. Although, actually, I think I did already kind of talk about much of this stuff on the prior slides. These are just giving concrete examples of the trade-offs, right? If I minimize communication, you know, the easiest way that we can minimize communication is to run everything on one core. Well, that's kind of an extreme example, right? Kind of the opposite of what we're going for here. If I'm trying to, you know, maximize my load balance, then we're pushing things in the opposite direction, where I'm going to have lots and lots and lots of itty-bitty tiny tasks that are going to have to talk to each other a whole lot in order to be able to accomplish whatever it is that they're going to accomplish. So the real goal that we're trying to get to is somewhere in between those two extremes. So let's talk about how we can identify and break down our problems into these concurrent tasks. The two major ways to think about it are data parallelism and functional parallelism, where the example I gave before with matrix multiplication, that's a very clear example of data parallelism. Breaking the actual data into chunks, in this case rows or columns or whatever the chunks may be. And again, it could be a single row or a subset of rows, right, depending on how big your matrices are, how many cores you have, right? So lots of different ways you can divvy it up. But that's a clear example of data parallelism. And actually, we like data parallelism. Data parallelism is a very common way of breaking things up. You're going to see it on homework assignments a lot as well. So this is really, when we talk about single program, multiple data, that is a very common way of approaching things, but not the only one. I think it's worth talking about functional parallelism as well. And for that, think of a pipeline. So a good example of this might be like doing some kind of video processing where I take a frame of a video and I want to run it through a bunch of different filters, perhaps. Each of those filters is going to be a different function, so I feed it into the first one, and then I feed it into the next one after that, and then the next one after that. That's a pipeline where each of those filtering functions might be running on its own separate core. So instead of breaking the data up and splitting that up across the cores, the data is actually flowing through each of the cores in a pipelined manner where the functions apply over it like waves, right? First, the first core applies its function, then passes to the next one, which applies its function. Now, the problem with functional parallelism, as you can probably imagine, it's very, very difficult, very, very hard to ensure that two or more functions are going to operate in the same amount of time for a given piece of data. That's a difficult thing to balance. It's much more difficult to balance. With data, you know, if I'm operating the same function across different chunks of data, that's actually much easier to balance. Just keeping the data size consistent, the size of our data set consistent across all of those cores. But with functions, that can be a lot more difficult to balance out. So the nice thing about pipelining, though, it does have its uses. It does have its benefits, its advantages. The nice thing about pipelining is that the data set usually doesn't matter. The size of the data set, I should be more clear, doesn't matter as much because all of the data is going to flow through. And so we get nice parallelism out of pipelining because I have multiple functions operating at the same time on different stages of my pipeline. That's where the parallelism comes from. So for things that require multi-step processing, pipelining is a good choice. We may see some examples of that throughout the class, but the vast majority of the examples that we see and that you hear about in the literature when it comes to parallelism are relying on data parallelism, which is breaking our data set into smaller chunks and running the same functionality on all of those chunks of data. Okay, so once we've decided how to decompose our problem into tasks, which is not a technical term in any sense of the word, right? It's very informal use of the word tasks. We're then going to assign these subproblems to threads, where the use of the word threads here, you can see the asterisks by it, is also maybe a little bit misleading. I'm not talking necessarily about a thread in the context of running threads on our CPU, like we're going to be doing on the next homework assignment. These threads could be, if we're using MPI, they would be the process, right? It's because MPI operates using processes, not threads. So try not to let your brain stick too much on that idea of a thread. What we're really considering here is, do I want to take all of these subproblems and assign one of them per core? Or, I mean, depending on how many cores I have, that could be very, very inefficient. Maybe I need to take a couple of these and bundle them together and ship them off into a single core, right? So it's somewhat independent of the problem itself. We're now kind of trying to bridge that gap between the decomposed problem to the actual execution units. I think that might be a better word to use than threads here, right? The actual units of execution in our parallel program. And we actually kind of briefly touched on this. Yeah, this is what I was talking about. Not just operating system threads. It could be operating system threads if that's what we're using, but it could also be processes if we're using a distributed system like MPI, or if we're talking about streaming computing, which we actually haven't talked about streaming computing in here much. It could just be a stream of instructions as well. That's probably for a later day, not today. And then, yeah, this is the point that I was trying to make, right? The assignment of tasks to our threads could be one-to-one, but doesn't necessarily have to be. And this allows us to think about our problem at different granularities. So using our matrix multiplication example, since that's just a convenient one, the smallest possible granularity would be a single row or a single column. I guess if you really wanted to, I suppose you could take it down even further to just a single element, like a single unit within that array or in that matrix. But I think most people would agree that unless you have a whole bunch of bajillion cores, that would be very inefficient. Packaging up in rows makes a little bit more sense, but maybe packaging up into 5 rows would make more sense than just a single row. So testing different granularities is going to be part of any parallel programming design task to figure out where that sweet spot is. It's going to depend on a lot on the system that you're using and the problem that you're solving in the architecture as well. There's not necessarily a formula or anything that you can use that can spit out, you should use exactly this data set size to get the best parallelism. Because some of these things are hard to determine at face value before you actually run the code and see how it actually works. And so then, once you actually break these up into their threads, is what we're calling them, they might map one-to-one with processor cores, but again, that's not necessarily required. If you're thinking about load balancing, for example, it could make sense if I have chunks of a problem, we're drifting away. Let's assume not matrix multiplication. Let's assume we have a problem that decomposes into different kinds of tasks, where one of the tasks is very floating point heavy, requires a lot of floating point operations, and one of them is maybe more symbolic kinds of arithmetic, right? Those are going to utilize different parts of our CPU. So we might actually be able to get away with running 2 of those, one of the floating point and one of the symbolic, on the same core without too much of a performance hit, right? Whereas if all of them are floating point, floating point, floating point all day, then we could easily overload our CPUs by assigning too many of those threads, too many of those floating point threads to the same core. So there are ways that we can kind of exploit this. In a lot of cases, though, especially in the cases that we see in this class, the tasks are going to be kind of homogeneous. They're going to look very similar to each other. There's not going to be a lot of different types of tasks. But if there are, definitely want to exploit that if at all possible. Okay, so we've then gotten to the next phase of parallel program design, which involves the communication piece. So this is orchestration, basically determining which threads need to talk to which other threads in order to get to solve this particular problem. So at this point in time, right, once we've decided that these tasks are going to live on these threads or these processes, we should then be able to determine who needs to talk to who. and when, in order for all of these processes to do their job. And that might lead us to shuffle those tasks around a little bit, right? Because the fewer of these arrows that we can have on our diagram, the less communication that we're going to have, and hopefully the better performance we're going to have. Within a certain degree, getting rid of all communication, though not a realistic goal, right? There's always going to be some. There's just not much we can do to avoid it. Even if we try really, 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 really hard to avoid all communication, it's probably just not going to happen due to things that are outside of our control, like the operating system interrupting our process to do operating system stuff, and then having to come back and having to fetch stuff from cache, having to fetch stuff from memory, things like that are going to work their way into our execution, whether we try to avoid them or not. So at this point in time, though, since we are talking about communication, this is where the programming paradigm really starts to matter. Just as a little refresher, our shared memory programs, communications are done by reading and writing to a memory location that is shared across those two cores, or more cores, depending on the chip that you're using. The unit of communication is a cache line, and whether we like it or not, we can't dictate when those cache lines get sent, right? We don't have control over the cache. That is not something that we as programmers have control over. That's all managed by the operating system. We can certainly write our code in a cache-friendly way that tries to utilize, caching as much as possible. That's why we typically tell people to iterate over our two-dimensional arrays in row major order, right? Because those arrays are written into cache in rows, not columns. So if I iterate down the columns, I'm going to be hitting the cache. I'm going to be hitting memory a lot more often. Whereas if I go down rows, well, the first element I read is going to call it to be pulled in cache, and then when I read the second element, I don't have to go back to memory. It's already in the cache, so it saves me all those trips to memory. So we already do things like that regularly, and honestly, when I say we, I should include the compiler in there as well, that is optimizing our code for these things too. We already do lots of things as programmers to try and maximize the cache effectiveness as much as possible. But there's some stuff that we're just not going to be able to do. The biggest thing, of course, is to manage our critical sections, because those are going to be the biggest bottlenecks that we have that forces everything to effectively be sequential, or at least not sequential, but to stall out while we're waiting for the locks to release as one process after another accesses that particular critical section. So in terms of minimizing shared memory concurrency, the critical sections are what we need to look at. With message passing, we have a lot more control over it. So I can't go to the OS and say, hey, make sure this line stays in cache. That's not a thing that I'm able to do. Maybe somewhere down in the kernel level, if you dig down deep enough, there's a way to do that. But if I'm writing, high-level language, that's not really something that I have control over. Whereas with message passing, I have control over every single communication that gets sent, which again has its pros and cons, right? Being explicit about it, we get to control the message size. That's actually pretty huge, right? When we're using shared memory, the message size is based on the size of the cache line. I can't make it any smaller or bigger. That's how big it is. That's how they communicate with each other, is by moving cache lines around from memory. So with message passing, I have a lot more control. I can turn the knobs a lot more. I can make my messages bigger or smaller depending on the problem, depending on how much data needs to move from point A to point B. Bigger messages actually generally are better because there is a certain degree of overhead for sending messages. We have to allocate buffers on both ends and then send the data across the wire, right? Which has some latency involved with it. So the bigger I can afford to make the message, usually the better. Of course, there are opposite extremes where if the messages are absolutely gigantic, then I'm going to run into problems there as well. But we have a lot more control over this. And then, of course, as I mentioned last week when we talked about programming paradigms, the fun part really comes when we've got both running in the same program, which if you're looking at machines in the top 500, especially at the top of the top 500, that's going to happen. That's basically a guarantee. Where on the grand scale of things, I'm looking at a bunch of server boxes in a room. Each one of those server boxes locally is probably a shared memory system with 16 or 32 cores on a chip sitting in one of those server boxes. But at a big scale, they're distributed because the 32 cores on this box can't talk to the 32 cores on this box unless I explicitly send that message over either Ethernet or probably more likely InfiniBand for the supercomputers, as we talked about last week. And so knowing how to do both of these things becomes really essential. And knowing which part of your code is going to be the shared memory part and which part of your code is going to be the message passing part becomes really, really essential. And also can be kind of confusing as well when you're mixing those two things together. This is a rule that we actually already talked about, and I showed you an example of it last week, but it's worth mentioning again, in part because I believe this is what you're going to be seeing in a week or so when we talk about homework 2, and probably also homework 3 to a degree, even though homework 3 uses OpenMP. Well, you can see I mentioned OpenMP right here on this slide, which is nice. The owner computes rule divides our results up based on which processor we are. So this was the example I showed, maybe you have it in your notes or maybe you remember last week, where every thread gets assigned an ID number, and I'm going to determine which part of the problem I work on based on my ID number. So if I'm crunching a vector of 100 values and I've got 10 cores, right? If I'm core number 1, I'm going to take values 0 through 9. If I'm core number 2, I'm going to take values 10 through 19, and so on and so forth. That is an example of the owner computes rule. And it's a nice way of doing things because we can distribute the data, the actual data set, to all of the cores. Or if it's shared memory, we don't even have to do that, right? If it's shared memory, if all 10 of those cores are on the same chip, I can just write my data set in one place on that shared memory, and then they compute, okay, I need to access the first 10 units, and then I need to access the second 10 units. And so we don't even actually need to explicitly do any more work than that to divide our problem up into smaller chunks. It's just automatically done based on our ID number. In a more distributed system, we can still leverage this, though, by doing what I was kind of speaking to at first, where I'll just take my whole data set and write it to all of the memory systems that are there. Now, do we have enough memory to do that? That's certainly a question you would want to take into account before choosing to do things this way. If you don't, then some more manual decomposition is going to be required, where you're going to have to physically take half of my data set and put it on this box, and the other, or maybe not even half, maybe just a tenth of it and put it on this box, and another tenth and put it on this box. But it's certainly much easier for communication purposes if I can have the whole data set available to all cores at all times, if we actually have the memory available to do that. So for some problem sizes, yes, this is great. For larger problem sizes, this becomes a little bit more problematic. But this has become such a popular approach that they've developed languages. I think I mentioned these last time too. Partitioned global address space languages, and I feel like I did kind of a mediocre job of explaining them last time. So I did a little refresher for myself. What these are is what they try to do is they try to take a distributed memory architecture, memory that is spread out across 10, 20, 1,000 boxes, and allow us to write a program as though it were shared memory. So from the programmer's perspective, I just write the program as normal, as if the code is running all on one box. And then when it gets compiled and ultimately decomposed and distributed to all of the actual boxes, the language itself, the compiler itself, takes care of saying, oh, okay, I've got 10 cores on this box, so I need to map this chunk of the data to that box. I've got 10 cores on this box, so I need to map this chunk of the data to that box. It's done on the compile level for us, really taking that workload out of our hands. That's a really nice, somewhat recent development in the world of parallel computing. The one that we're going to be using, though, is OpenMP, which does do this, but on a shared memory kind of level. We're not going to be using it on a distributed system, although you certainly could. Okay, and then the last step of parallel program design. Once we've gone through all of the previous steps, this is where the actual hardware comes into play. We have to take all of these threads or processes or whatever they are and actually map them. So this process is going to go on, these are actual physical boxes, right? So this task is going to go on this box. This thread is going to go on this box. This thread is going to go on this box. And again, the thing that we're worried about here is communication. Because some communication is necessary. You can see that a lot of times, these aren't necessarily in any particular order, but if I see that there are two tasks that need to communicate with one another, like these two right here that have the arrows going back and forth, well, I'm probably not going to want to put this one on one end of my server room and this one completely on the other side of my server room, right? I'm probably going to want to keep them somewhat close together so that communication isn't going to have to travel any farther than it has to. That's the idea behind the mapping stage. How do I actually utilize the physical layout of my machine? This kind of ties back into something that we talked about last time as well, when especially our massively parallel supercomputers aren't going to be networked in the traditional sense. They're going to have their own custom interconnects, with the torus being one of the more popular ones that we saw, kind of like a grid shape, right? Which works out well. Me using matrix multiplication as an example is not just for convenience, it's also what a lot of these supercomputers are doing. If you look at, for example, large language models, that's big old giant matrices being multiplied together. That is how they make those. That is how those are developed. That is what's running on these supercomputers to develop the next AI models. So not just a convenient example to use, but also practical. That is still by far one of the more common computations that we are doing on these big old giant machines. And you might say, well, yeah, we can do that on little machines too. Clearly we can do matrix multiplication, but we're talking big matrices, right? Giant ones. So that's why having these supercomputers really is a necessity to compute these models. Although, for how long will that stay true? That's another interesting question to think about. Let me pause here. Are there any questions about these steps here? Because I think we're about to switch gears a little. Oh, I do have a little bit more to say about mapping, I guess. But still, any questions that I can address, or anything that was not clear that you would like me to go back through one more time? I'd be happy to do that, if so. If not, we're getting closer to actually taking a look at some actual examples of parallel programs. Let me finish up the mapping phase first. I was a little bit premature there. On shared memory machines, we can just let the OS do it, but with paradigms like OpenMP, we're actually using those pragmas right in our code, and we're going to get a lot of practice with OpenMP when we get to homework assignment number 3. I'm going to have a whole day where we just go through examples of OpenMP code, which is one of my most, I love that day. That's one of my most fun days in this class. I'm really looking forward to it. And the nice thing about this is that, anybody know what NUMA stands for? Anybody familiar with that term? Yeah? Non-uniform memory architecture. Yeah, so anything where we have non-uniform memory architecture, meaning that different cores are going to have access to different parts of our memory. Which is often the case in these large distributed machines. All right. So let's talk about actual execution. Here, we're actually looking specifically at an example of decomposing a matrix where we have some form of communications in the terms of I need to know what my nearest neighbor's values are. So if I'm at a particular point in this array, in this matrix, in order for me to do my job, in order for me to compute what my value is, I have to know what this guy's value is, I have to know what this guy's value is, and this guy and this guy. Or you could even do it for the diagonals as well, which might be appropriate in some problems that you're trying to solve. But the point we're making here is that there is some communication required, although where is that communication happening? If we think of our decomposition as subsets of the matrix, notice here we actually didn't choose rows to decompose. We chose subsets, so submatrices of our matrix, and mapped these each to the process, which for nearest neighbor communication is a pretty well-known, well-studied problem. Makes a lot of sense. Where's the communication need to happen? Only on the edges, right? So if this is a process that's taking care of this chunk of my matrix, well, I'm going to have to communicate this entire bottom row down to this guy, and I'm going to have to compute this entire left column over to this guy in order for it to be able to do its job effectively. But anything that's in the middle, we're good to go. I don't need to communicate that data anywhere. Contrast that with, if we were using my previous example of breaking things down into rows, that could really complicate the way that communication works if we did that way. Imagine P0 stretching across the top and then having to communicate all of that stuff down to the process below, and the next one communicating all of that down to the process below. The number of processes that we are communicating to is higher by doing it this way, right? Because I have to communicate in all four directions in some cases. But the messages that I'm sending are smaller. So that's an example of the trade-off coming into play, right? Sometimes more smaller messages is going to be more efficient, more effective than fewer amounts of larger messages. This is actually the kind of decomposition that we'll see when we get to homework 3 with OpenMP. And the nice thing, too, is even if we need to know, let's say that the problem requires us to know the data from over here to get to from P9 to P11 or P8 to P11. Some problems might require that, right? Some problems may require not just the most immediate neighbors, but even the faraway neighbors as well. In the case of the n-body problem, which I believe will be the basis of our final homework assignment, it involves looking at a bunch of planets or a bunch of stars or bodies, let's call them, right? Because it's the n-body problem. And how do they move? How do they move over time? Well, instead of taking into account all of the planets that are super far away from me, I can just kind of group them together and compute their center of mass and then transmit that one value instead of transmitting the individual value for all of the different bodies. And so that's kind of what we talk about when we say long range, but it falls off with distance. For these neighbors, yeah, I probably am going to communicate all of the individual data points over here because they're close to me. They're going to have the biggest influence, the biggest effect on me. But as they get farther and farther away, I'm more likely to consolidate this data and transmit it as a single value as opposed to all of the individual values to save myself some execution time. Is it a simplification? Yeah. Does it work for some problems? Also, yes. So those are the kinds of shortcuts that we're looking for when working on these massive problems. This will also, you might be wondering, well, galaxies aren't two-dimensional like this diagram is, but it does also expand into the third dimension as well, if that's what we're actually interested in. Notice, though, that if we assume that this is, for example, if this wraps around, we might. So maybe this is like a sphere in a sense, right? We then would have to communicate this over to here because those would actually be neighbors. So That's another configuration to take into account. Lots and lots of different ways to decompose and try and exploit the different forms of communication. Let's talk about another approach that is commonly used with massively parallel programs called the Monte Carlo simulation. Are you familiar with Monte Carlo simulations? I see a few hands. That's good. So Monte Carlo simulation uses random sampling to solve a problem for us. You see some examples here with optimization, meta-heuristics. So I used to give a talk about, oh gosh, it's been a few years. Maybe I shouldn't have brought this up because my memory is a little bit too rusty. Simulated annealing, where you're trying to figure out if, imagine you have a plot of some function, right? And you're trying to find where the absolute minimum is of that plot. And you might get tricked by finding a dip that looks like a minimum, but it's not the absolute minimum. So with some random degree of chance, you have to say, well, I hit the minimum, but I'm not going to stop here. I'm going to keep going. That's an example of a meta-heuristic, of just sometimes randomly rejecting what looks like it might be a correct answer, to keep exploring a little bit to make sure that it actually is the thing that we're looking for. Risk analysis, integration. We'll see an example of integration actually on the very next slide. It's one of my favorite examples. But all of these, what they do is they rely on random numbers. So, and they follow a similar pattern. All the Monte Carlo simulations have kind of the same general approach. We have to first know what our inputs are going to be, and then we're going to generate random inputs from some probability distribution. Could be uniform. I think the example on the next slide is an example of a uniform distribution or a Gaussian distribution, or it might just be some empirical distribution that is, non-standard that we're trying to model based off of measurements that we've made in a lab somewhere. Could also be the case as well. But then we're going to perform some deterministic computation on those inputs. So based on the random values, we then deterministically compute what we're after and aggregate the results. Let me show you a concrete example. One of my favorite Monte Carlo examples is estimating pi. So the way that this is sometimes framed is computing pi by throwing darts. It's a pretty classic example. Imagine that we have a dartboard here with a square and a circle. I know dartboards are typically circle, but we have this nice little unit square here as well. The idea is that I'm going to throw darts at this. Sometimes they will land inside of the circle. Sometimes they will land outside of the circle. If we take the ratio, well, I'm getting ahead of myself. We're going to use random numbers. So I'm going to throw these darts randomly. The easiest way to think about this, if this is 0, 0, and this is 1, 1, I can just generate two random values between 0 and 1, and then that will give me some random xy point on my dartboard. And those darts are either going to land inside the circle, or they're going to land outside the circle, as you can see on this diagram. We've simplified this a bit by just looking at one quadrant, but the idea is still the same. If we take the ratio, there's some algebra involved here, but if we take the ratio of the darts that land inside of the circle to the total number of darts that are thrown, that allows us to approximate specifically pi over 4. And there's, again, some algebra there to get there. The area of the circle as it relates to the area of the square, you can see the algebra. I'm not worried about the algebra. I'm worried more about the Monte Carlo approach to the simulation. But what we end up doing is we end up essentially keeping these points and chucking these ones out. We don't care about them. They're not helping us at all. So if we do this for enough values, we have to throw a lot of darts. If you only throw 2, you're not going to get a very good value for pi. You have to throw a lot, thousands. So that's kind of another important point with these Monte Carlo algorithms, right? Because of the randomness involved. Just doing it a few times is not going to be good enough. You're relying on the law of large numbers here. It says as we do Even if we do a lot of random things, if we do it enough times, they will eventually converge to the distribution. In this case, uniform distribution should be evenly spread out roughly across the entire space. The nice thing about doing this is that each one of these is independent. So each dart throw is independent. So if I want to throw 1,000 darts and I have 1,000 cores, each core throws one dart, boom, I can do all of that in parallel, independently of one another, as opposed to cranking it all through one single core. This is an integration. I'm really just integrating the area under this circle, okay, to help me compute the value of pi. This is a little toy example. We actually do this in the intro class because you can do this with a couple of for loops and an if statement, I think. It's not terribly complicated to code up, but it's a great example of a Monte Carlo problem. It has all of the components, all of the pieces are there. But let's take a look at maybe a bit more complicated one. Here, we're setting up actually Laplace equation. So we have this wonderful chunk of whatever it is. I don't know what it is, some piece of metal, right? Maybe it's floating around in outer space somewhere. And we know what the temperatures are on the boundaries. So these are in Kelvin, I'm assuming, or maybe, yeah, something like that. We know what the temperatures are on the boundaries. The question is, what is the temperature in the middle? Because I want to make sure that the whole thing isn't going to fry and fall apart in outer space, right? I want to make sure the whole thing is going to remain stable and do what it needs to do. You can do this in a deterministic way. You don't need to use a Monte Carlo simulation to do this. The problem, somewhat, is that if you want to do it deterministically, this is an irregular shape, right? So on the homework assignment that I give you, I'm going to give you a nice rectangle to run Laplace on, because obviously the numbers are going to work out a little bit nicer for a rectangle than for a weird shape like this. But when you have a weird shape like this, which of course is going to be more realistic to real life, because not everything in real life is rectangles. Some things are, but not all things. Well then, it gets a lot trickier to use that deterministic approach, to visit each one of these. We would essentially overlay a grid over the entire thing. And then this is an example of a nearest neighbor computation, if you do it the deterministic way, where I know the values on the edges, so I start by computing the values that are just inside of that, and then I compute the values that are just inside of that, and then I compute the values that are just, so it kind of sweeps across the whole surface until eventually it will converge, the numbers stop moving, and at that point we say, all right, that's what it is. That's what the temperature is going to, the temperature is going to be across the entire surface of this particular piece of material. Let's say, though, that I don't really care about every single point. Maybe I don't care about every single point. Maybe I'm just worried about a few key parts of it. In that particular case, I think a random walk might be a better way to go. Or even for an irregular shape like this one. You can see I've got a nice rectangle here. Maybe I could do it deterministically for this one, but then for some of the weird spots, I could use a random walk to help me figure out what those points are. So here's how this works. For the point that we care about, we just start moving in random directions. I'm going to generate a value between 0 and 3, right? 0 is go up, 1 is go right, 2 is go down, 3 is go left. And so I just keep doing that. All right, I go up, I go left, and you can see I just wander about until eventually I hit an edge. I hit a known value. I know what the temperature is on the edge. I write that down, 400 Kelvin. Okay, but this is a Monte Carlo simulation, so I'm not just going to do it once and assume that I'm done. I'm going to do it a whole bunch of times. So the next time I do the random walk, maybe I end up on this edge. And the next time maybe I end up on this edge. And then maybe I go back up here again on the next one. So I'm going to do this walk thousands of times, right? Thousands and thousands of times. And then once I write down all of those values, I'll aggregate them, typically averaging them together. And that will be the value for that center point. If we do enough walks, right? it will converge to the actual temperature the same way that it would if we did it systematically across the entire thing. And it allows us then to actually skip computing all of these if we want to. Now, this has some trade-offs, right? If I wanted to know the temperature across the entire thing, I think this is a bad approach. If I'm trying to do a whole bunch of random walks at every single grid point, I think that's going to be less efficient overall than doing it the systematic deterministic way where I just compute successive rings until I reach convergence. Because these walks, they can be short, they can be long, they can be all of the above, right? It's even theoretically possible, though somewhat unlikely, for them to just sit here and spin forever and ever and ever and ever and ever. Right? That's also a possibility. In practice, they almost certainly do end within a reasonable amount of time for a well set up Monte Carlo simulation, but you can imagine for a very large grid or very tight grid, that's going to make your walks take a lot longer to converge, and that's something that we need to be considerate of as well when we develop these programs. So, but if I'm just interested in a few critical points inside, this is a great tool that can save me a lot of time and effort from computing points that I don't really care about, or points that, maybe these ones close to the edge are just easy to figure out because they're so close to the edge, so I don't need to do random walks for that. That's kind of silly. If I do a random walk from right here, it's almost certainly going to hit this edge almost every single time. Yeah, maybe you might get some random one that goes all the way up to the top, but that's not going to happen very often, right? So we can actually combine these things, do a mix and match, use a deterministic approach for the low-hanging fruits, and Monte Carlo simulations for some of the more difficult inner points, some of the more irregular points that we come across. And this, by the way, is going to be a little extra credit for you coming up on one of the future homework assignments to code this up. But we don't need to worry about that right now. We haven't even got through homework 1 yet. So let's talk about random number generation, because this is actually a tricky thing to deal with in parallel programs as well. And will be relevant to you if you do want to tackle that extra credits, perhaps, on future assignments. True random numbers are difficult to come by. There are some natural processes that are true random. One of my favorites, random number generators that I've seen, is a lava lamp. Lava lamps are true random. There's a website, I think, that will take a picture of a lava lamp and use that to give you random numbers. It's pretty cool, but also very inconvenient to do it that way. I don't want to wait on a lava lamp to give me random numbers, especially if I need a whole bunch of them, right? I would need a whole bunch of lava lamps. That's impractical. They look cool, but not very practical. There are other ways you can do it. Radioactive decay, that one potentially dangerous depending on what radioactive substance you decide to use. Lots of physical phenomena that you can use, but physical phenomena and computers, right? That's more difficult, not necessarily convenient. So pseudo-random numbers, very easy to generate, but they're quite deterministic, meaning that if I get a certain part of the series, and it doesn't even have to be that much of the random number series that's generated, even with just a small chunk of that random number series, we can predict what the future random quote-unquote values are going to be with just a small set. That's a Taylor series expansion in a lot of cases, right? Which people learn about in, is that Calc 2 or Calc 3? I don't remember. It doesn't matter. But, we're teaching it to our undergrads, so not difficult for a hacker, for example, to figure out if they're so determined to do so. The way that these pseudo-random number generators work, for example, or the way that we use them in practice, rather, I should say, is that we're going to generate, we actually start by generating uniform random numbers on a range from 0 to 1. Well, it doesn't have to be 0 to 1. This is how it would be done in Java, for example. Math.random gives gives you a value between 0 and 1. In C, it's a little different. You get a random integer between 0 and max rand, which is just a constant, just a system constant, which is usually actually equivalent to max integer size. So if you need random numbers bigger than 2 billion something, well, you got to figure out a different way to do it. But for most applications, that's sufficient. But that's uniform randomness, which is fine for some things. If I'm flipping coins, right, that's uniformly random. 50-50 shot, heads or tails. A lot of things that might apply to. But what if I want a Gaussian distribution? Or what if I want an exponential distribution? Or some other kind of distribution that is not uniformly random? We have to then transform it. We have to apply some math to this uniform distribution. If I want Gaussian, right, we want that nice bell curve to show up, which clearly this is not. So we have to apply a transformation to it, which, again, the math, kind of outside the scope of this class, that's a library call for a lot of this stuff to generate for us. The problem is, well, hang on, I'm not quite to the problem yet. Here's how it's actually computed. This is done via a recurrence relation where I get to choose m. M is the range of my random numbers. So if I want random numbers between 0 and 100, I would actually pick m to be 101. Because we're taking the modulus, which means it can never actually be m, it can only be up to 1 less than m. The values of a and c are, you can see a multiplier and an increment. Those are constants. We actually don't have to pick those. There's tables that exist of a and c values. If you're interested in creating your own pseudo-random number generator, you can just look them up. I mean, you really could compute them yourself if you really wanted to, but that's a solved problem. Nobody wants to actually compute those anymore. We can look those up from a table, and then x of the n, there is our seed value. So to get the next value in the series, right, I just compute this. So here's my seed value. That's my a seed number for those who aren't familiar. Anytime I use a random number generator, I have to start it off with a seed, which is good and bad. Using seeds is really nice because if I ever want to replicate the same random numbers, I can use the same seed value, and I'm guaranteed to get the same seed numbers back out. So it allows me to verify certain kinds of randomness, right, if I want to have control over that. The downside then being that, of course, if I am computing the next random value based on the previous random value, that's actually what makes it so easy for us to crack the pseudo-randomness and figure out, oh hey, the random value 5 steps from now or 10 steps from now, I can just crunch those numbers. It's really just a multiplication, an addition, and a modulus. So it's not hard for anybody, given enough of that series, to decompose this and then know all of the random numbers that are about to come up. If you're running software that relies on that randomness for correctness, such as, gambling software, for example, you wouldn't want people to know what the next random numbers are going to be. That would be bad for business. So pseudo, it means it's called pseudo for a reason. For most practical purposes, they're random enough. If I'm doing cryptography, if I'm doing anything where the randomness is crucial to the, outcome of my program, they're not random enough. They definitely are not random enough. But that's a different class. What I am worried about is the parallel version. What I'm worried about is the parallel version. I want to be able to use pseudo-random number generators in my parallel programs because they're quick, they're easy. A lot of the times I don't need that guaranteed randomness. It's not necessary. The pseudo-randomness is enough. But how do I do that effectively with these pseudo-random number generators? Well, one idea is if I have 4 processes that each need random numbers, I'll just use a different seed for each one of them. And on its face, that might seem like a good, reasonable approach. But there is a potential problem. Can anybody think of what the problem might be with that approach? So much of it depends on the seed number. What if the seed number that I pick for this process happens to be very close to the seed number that I picked for this process? just by bad luck, let's say, right? That means that the random numbers generated from process 1 and process 2 are actually going to be almost identical to each other. They're not going to be independent at all. They've hit on the same series. Maybe they're on different parts of the series. Maybe one of them is a few random numbers ahead in the series than this one is. But they're on the same series, and they're going to get the same random values back out, which means that those two effectively are not independently random anymore. They're generating the same random values. This is a big, big, big problem when trying to use pseudo-random number generators with parallel programs. That seed number, by the way, we can pick it ourselves. It is possible to manually feed it in. But typically, it's chosen by the computer based on the clock. So it usually just uses the last, I don't know how many digits, 3 or 4 digits of the CPU clock as the seed. Which, again, if you fire off all 4 of those processes very close in time to one another, could lead exactly to that situation I was describing, where they get very similar seed numbers, right? If these two fire off a few nanoseconds apart from each other, that clock's not going to have moved very far forward. Those last few digits are going to be very close to each other. They're going to be generating random numbers, yes, but really the same random numbers across those 2 processes, or even across all 4 processes, and that's bad. That's going to lead to bad results for our Monte Carlo simulation. So, how do we deal with this? We use what's called a parallel linear congruential generator, which is a huge mouthful. Here's how it works, though. Again, I'm not worried too much about the math down here. I'm worried more about how it works. If these are our processes, so I've got 8 of them in this particular example, one way to think about it is, okay, here's a seed for the first process, here's a seed for the next one, here's a seed for the next one, here's a seed for the next one. But what you can see is that we're not just going to use the next value. So this process is not just going to use the next random value that it generates here. It's actually going to skip ahead. So it's going to realize that, oh, hey, these next 3 seeds, these next 3 random values are going to be used as seeds for these processes. So I don't want to use these. I'm going to skip ahead 4 values to use this next one. And then after that, I'm going to skip ahead 4 values. And then after that, I'm going to skip ahead 4 values. You can do that in a couple of different ways. You can just burn 3 values, generate them, and just toss them away. But that's kind of extra work that doesn't have to be done. So this equation down here is the math. Actually, the math has more to do with this A factor. I think you just scale the factor A up by how many numbers you want to skip ahead to generate those values in the series. Which again, the math is somewhat outside the scope of what we're talking about today. And so now with our parallel congruential generator, we're not using every single value in the series on a single core, but we are using every single value in the series distributed across all of our cores, which prevents any of these later processes from reusing random numbers that have already been used on previous processes. So this solves our pseudo-random number generation problem. And part of the reason why I am telling you all of this is, again, because this may come in handy on a future homework assignment that is coming up in the next couple of weeks. Or it may not, because as you know, you kind of get to pick and choose which problems you work on. So if you don't choose a problem where this is relevant, then maybe it's not useful to you. But some of them, you may need to use this. Other distributions are pretty straightforward. So for an exponential distribution, you just take the log, right? And divide by your lambda parameter for your exponential distribution. Other distributions have more complicated math, but again, we're not doing that math ourselves. We're cranking that through a library, so I'm not too worried about understanding the math more than I am understanding the process. And yeah, and so then what we can do as well is what's called the rejection method, which is actually very similar to what we were talking about with the Monte Carlo pi simulation, where we have a target distribution, and I will generate random numbers, and if they appear, if I'm going for a Gaussian, right, I will generate random numbers within my range, whatever range I care about, and if they land underneath my nice bell curve, okay, I keep those ones, and if they land above my bell curve, I say, well, I'm going to reject those. Those don't match my distribution. With the downside, of course, being those are wasted cycles, right? Any numbers that you generate but don't actually use, it's just pure loss. So does it get you where you're going? Yes. Is it the most effective way to get there? Not necessarily. But again, a lot of this stuff is library based these days. We just have to know what distribution our targets are and find the appropriate library to use to perform these transformations for us. I think this is the end of part 1 of today. Does anybody have any questions for me about what we've covered so far? If not, it's break time. So we'll go ahead and take our customary break. 6:46. Yeah, we'll plan to regroup around 10 minutes or so. So around, we'll say 6:57 or so, give or take a minute or two. Grab a drink. Somebody was asking about a vending machine earlier. There is a vending machine. If anybody needs a snack, I can tell you how to get there. Otherwise, I'm going to shut up now. Thanks for listening.